Hi guys, so in this video we'll be speedrunning chapter 1.3 and 1.4 of the bigger chapter called Motion Forces and Energy, which is chapter 1. So this is the syllabus for O levels, but for IGCSE, as the content is same, you can use this video to study IGCSE as well. The only difference is basically the syllabus layout. The layout is probably different, where point 6 goes to point 1 and point 1 goes to 6. Not exactly, but basically, a slight layout change. That's about it. The content is exactly the same, so yeah, you can use this video for IGCSE as well. So let us start, and let's see if Z notes works. Before starting the video, I tried to check Z notes and it did not work. Well, it works now, so we'll be using it. So we'll be using the IGCSE notes for physics, theory, chapter 1. Let's scroll down a bit. Okay, mass and weight. We found this. Let's take it over here. Let's close this, close that, and we're done. So sorry for the flashbang. Let's start with point 1. State that mass is a measure of quantity of matter in an object at rest relative to the observer. So one of the first keywords here, mass, is a measure of quantity of matter in an object relative to the observer. What does this mean? So this is a definition for mass, and when they ask you what is mass or define mass, then you have to write this. Mass is a measure of this. So quantity of matter. If you have studied physics before, matter basically means the amount of particles or substance in an object or something along that line. So when they say quantity meaning the number of matter or the amount of matter. So let's just say you have a box, and this box is made out of wood, and the wood is made out of different chemicals, and if you zoom in and in, you get to the atomic level. So these are your particles, and mass is basically meaning the amount of particles or the amount of actual matter you have in your box. This is the measure of the mass. So if you had more particles in your box, your mass would be, let's just say, 20. If you had less particles in your box, your mass would be 10. The box size is the same. The size does not change. Okay. The size is similar, but the amount of particles change. So the particles are more tightly packed in, right? Okay. So now we know what mass is, the amount of matter in an object at rest relative to the observer. Why at this part, and what does this mean relative to the observer? So let's just say this box is down here and you are standing a bit farther away. When you look at the box needs to be stationary, or it should appear that the box is not moving. How do you achieve this? Either you stand still, or let's just say the box is moving this way, you also run this way. So if you if both of the box and you run this way, then to you the box will remain relative to you, the box will be stationary, as you are moving the same speed as the box, right? So the box isn't moving this way or moving backwards, so the box is still. To you the box will look like still. But if I, a third person, come in to the picture, then I can see that you are also moving this way and the box is also moving this way. So to me, a third person, you two are moving, but let's just say the person who is observing the box, right, to him the box is stationary. So this is why relative to the observer, you as an observer, it should be stationary to you. And why should it be stationary when you observe a box or a object? Why should it be stationary? Let's just say the definitions go a bit deeper because of Einstein's relativity and whatnot. And to be honest, I do not myself fully understand or grasp the concept of why it should be stationary. But let's just say if a object is moving, you cannot actually properly tell the mass on paper. I do not know why, please do not ask me. So now we know why it should be relative. Let's move on. And when they ask you for the definition of the mass, right, you just only have to write this part. You have to, you do not have to write this part relative to the observer. You should only write that mass is a measure of quantity of matter in an object or the amount of particles in an object. Boom, done. Like nothing more is needed. Well then, moving on. State that the mass of an object resists change from its state of rest or motion. So keywords state that mass of an object resists change from its state of rest or motion, and bracket inertia. So simple translation would be, let's just say a box is in free space. This is not even on earth. It is on, it is in free space above the earth, and there is no gravity, no nothing. A box is stationarily standing there. So if you try to move the box will resist, right? It will push you, push this way backwards and whatnot. So this is what we call inertia, I guess. Basically, any object matter which has mass, right? Anything that has mass has a tendency, or let's just say has a habit of resisting any change, right? If you want to move it upwards, it will resist. If you want to move it downwards, it will resist. It will want to stay as is. It doesn't want to make any change to its motion. And so now we have considered that the box is stationary, it does not move, right? It does not move, but you're trying to move it, and so it will resist the change. What happens when the box is already moving? Let's just say towards the right? The box is already moving. Now what happens? So now if you push the box towards the left, right, if you push it towards this way, the box will obviously resist the change. Why? Because it is always already moving towards the right. And then if you try to move it towards the left, the box will obviously, you know disagree with you, let's just say. And you might be surprised to know, but if you want to move the box more towards the right with more speed, the box is still try to resist you. Meaning the box is going towards the right with, let's just say, 20 meters per second. If you want to, increase the speed, the box will resist you. You have to, use energy, or you have to, let's just say, convince the box to move faster. And this convincing is going to be the energy you are giving to the box. You cannot move the box faster without giving energy. So this is the main concept, that if a box is moving, it will keep moving, right, until you stop it or try to change its speed. And if the box is already stopped stationary, then if you want to move it, it will still resist the movement. The box basically will resist anything. So this is the concept of inertia. Resist anything and everything, honestly. So to its, state of motion and state of rest or motion. So it could be at rest and it could be in motion, as we have observed both of the scenarios. So point 2 done. Let's just see point 3. Know that weights and therefore mass may be compared using a beam balance or equal arm balance. So if you ever went to a shop and if you want to buy, let's just say, 1 kilogram of salt, you either get, let's just say, a seal bag, or you can buy it in a, I don't know, open container where they have, like, let's just say, 50 kilogram big bags of salt, right? These big bags of salt. And you only want to take 1 kilogram from this open bag, then they have to measure it out. How do they measure it out? They use the thing called a beam balance, equal arm, or anything of that sort. So let's just see. This is the beam balance. This looks a bit prehistoric or whatever, it looks a bit old. If any of you have seen this, you might have seen this on TV, on, let's just say, some kind of law and crime show where they have this in the, courtroom, not on a, I don't know, grocery shop. It's fine, whatever, the purpose is same. So you put 1 kilogram mass on this side, let's just 1 kilogram of metal weight, and this metal weight is already calibrated to be exactly 1 kilogram, right? And then you have to put a bag over here and slowly pour salt on your bag. So when these two hands reach the same level, right, at the same level, then you have 1 kilogram on your left, you have 1 kilogram on your right, as they are, both on the same weight level. So this is how you use this beam balance thing. And equal arm beam balance, same thing. Now describe how to determine mass using an electronic balance. And honestly, electronic balance is pretty easy, right? You just take the electronic balance and stand on top of it, my guy, like nothing major. Yeah, this is your electronic balance. This will be the, meter or whatever, digital meter, and it will say, let's just say 10 kilogram is your mass. And yep, yeah, more or less same. More or less only this, nothing, let's just say deep here. You just buy the electronic mass in and stand on it. I don't know what they want here to describe, want you to describe, but we'll see in the notes if something extra is added. For now, let's move on to point 5. Describe how to measure weight using a force meter. So keyword being force meter. So in a few chapters we will learn what is force, but for now let's just remember that force is measured in newtons. So force has a unit, and that unit is called newtons or capital N. And this force meter will give you the weight in newtons. And then you might be wondering, what is the weight? We first look at mass and now we look at weight. So now we have to understand what is the difference between mass and weight. Mass is the amount of particles, as we already know. What is weight? Weight is the gravitational pull on the mass. So let's just say this is the earth, a bit goofy looking, but still the earth, and a mass is over here. So the earth will pull the mass towards its center, obviously. And if you're standing, let's just say you are the person standing here, you will be pulling, the earth will be pulling you towards its center. And this pulling force will be something you get, you can measure in newtons. And for us, it will be 9.8. And if you go to A levels, it will be 9.81, more or less. So 9.81 newtons. Almost 10. So what is this 9.81 newtons? Imagine you have 1 kilogram of mass, right? You as a human have 1 kilogram weight. Let's just assume, yes. You have 100 kilogram weight, that does not matter. Let's assume you are 1 kilogram and then you are standing on top of the earth's surface. You will be experiencing a force of 9.8 newtons downwards. The earth will be pulling you. If you have 2 kilograms, then just 9.81 into 2. So now I think you get the point. Mass is a matter of fact, because mass is the amount of particles you have in your body, and this cannot change. But the pulling force of gravity, right? This is a fundamental force. Is It is not a matter of fact. You are not born with gravity pulling down. You are born, but if you chose, you could be born on the space, right? I don't know, International Space Station. So more or less, this force, you have to choose to act with this force, or whatever, you have to come into contact with the gravitational force to get attracted by it. And this force, you might imagine, is only working on the earth. And if you go to the moon, right, this force will be different. This force will be like 1/6. I exactly don't know how much. Let's just say 3 newtons. On the moon, it will be 3 newtons per kilogram. So 1 kilogram will be pulled down to the moon with 3 newtons, let's assume. And so now you know why in the moon, when you jump, you can jump much higher. Why? Because gravity is pulling down less. And that is more or less the difference between mass and weight. So mass and weight are different thing. All this time when you use the digital meter or digital balance to measure your own weight, right? People call it measuring your own weight. You actually are measuring your mass. Mass comes in kilograms, kg, and weight comes in newtons. So when the digital electronic balance, right, gives you kg, this is your mass. And if you want to measure your weight, then you just multiply it by 9.8. into 9.8, and then you can get your weight. Finally, tangent aside, how to use a force meter. What is a force meter? This is a force meter. So you have a hook and you have this belt hanger thing. So you take this hook and you just, let's just say, hang it with a nail or something. Then you take this belt and tie a rope around it, and then take that rope and then tie a weight around your, or take that rope and tie it around a weight. So after you do all this setup, tie the weight on the rope and whatnot, then let the weight just hang on this meter, right? So the rope will be pulling the meter on one side, and the, let's just say, nail will pull the meter upwards. So then this meter will measure how much force the weight is pulling. So this is how you use this Newton meter. And obviously it will give out a reading in newtons, which is force. And you already know that force is a bit different than mass and whatnot. Sorry. So yeah, now we can calculate gravitational field strength. So let's first understand what is gravitational field strength. Define gravitational field strength as force per unit mass. Recall and use the equation this. So as we have already learned, force per unit mass. So 1 kg is your unit mass and force will be 9.8 newtons. So force per unit mass, we already know how that looks like. Recall and use this equation. So if you want to find out the field strength, take your weight, which will be 9.8, divided by 1, which will be your mass. So gravitational field strength would be 9.8. Let's just write here 9.8 Newton, 9.8 Newton per kg, right? This is the gravitational field strength, and it's, how should I say, unit 9.8 Newton per kg. So every kg you are adding to your body, gravity is pulling down with 9.8 newtons. So then you might be wondering, okay, heavier people cannot jump that high, you are saying. Well, yes, but also no, there is a bit of a nuance there, and we will look at it a bit differently later. But more or less, yeah, heavier objects will, or any object that has more mass will be pulled down more by gravity. That is a universal fact. So the shortened formula is given here, and know that this is equivalent to acceleration of free fall. Why is this acceleration of free fall? And what is acceleration of free fall? We have learned before that if you are falling through the air, so only due to the weight of gravity, right? Not air resistance, no nothing, no outside force is acting on you. Only the force of gravity is pulling you downwards, right? Then you will be accelerating at 9.8 meters per second square. You will be accelerating at this speed as you are falling downwards. So this is what they mean by, and know that this is equivalent to the acceleration of free fall. Equivalent, exactly equal. State that a gravitational field is a region in which a mass experiences a force due to gravitational attraction. So the Earth is here, and the gravitational field can actually spread much more, outside of the Earth's surface. So the moon is, let's just say, here, and believe it or not, gravitational energy, right? This field actually stretch out to infinity. So this field will actually try to pull you towards the Earth from infinity, even if you're infinitely far away. The only problem is when you're infinitely far away, the strength is so minuscule, the gravitational field strength is so minuscule that it's almost close to zero. So that is why planets from outer space do not come hurtling towards the Earth and crashing to the Earth, because they're very far away. Very far away means, the actual strength of the gravitational field is very low. And then the universe is also expanding, which is another topic. So yeah, there is like negative force. Gravitational force is not even positive, it's not even zero, it's negative. Yeah, let's move on. So in short, just remember that gravitational field is a region in which a mass experiences force due to gravity. Just memorize this whole thing. You have already understood why that is and what this is, right? Just memorize this thing and just write it up, straight and simple. Now we move on to 1.4. 1.3 is done. Okay, we can look at the notes. So this is the notes. Let's like speed read it. The mass of an object is the measure of quantity of matter. Yeah, sure. So they have kilogram to gram. Sure, sure. So mass is different from weight, which is a gravitational force on an object with mass. Yeah, sure, we understood that. So a bunch of units and whatnot, and dependency. You can pause it, read it if you want. I'm just gonna speed through it. So gravitational field. Yeah, yeah, I think we covered everything. Now let's move on to 1.4. Define density as mass per unit volume. Recall and use the equation. As you have probably seen before, I used a box, and this box had particles in it, right? And when I said there are more particles in the box, but the size does not change. So what does that mean? More amount of particles are, packed inside this box, tighter and tighter. So this is what they mean by mass per unit volume. So the number of particles you squeeze into this box, right, the density goes up. Why? Because the box itself, right, it does not increase in size. It is the same size. You're just pushing more and more particles inside it. So mass is increasing, but the volume is not. And the formula is basically, I don't know, inherent, as it basically meaning it speaks for itself. There is no derivation of this formula. Not yet. We can look at the derivation of things later. So just remember this formula. Density equals mass by volume. What is density? Amount of matter per unit volume. So let's just say 50 particles per 1 cubic meter, 1 cm cube, right? So what is 1 cubic meter? Let's just say you have a box, then write down or draw down a three-dimensional box. So when you draw down this three-dimensional box, the area inside or the volume inside will be, let's just say, 1 cubic meter. Why? Because every length, right, this length, and this length will be all 1 meters. So when you multiply all of them together, the area volume inside, right, the volume inside will be 1 cubic meter, sorry, 1 cm cube, not, so it will be 1 meter cube. So this is what density means, amount of matter per unit volume. Describe how to determine the density of a liquid. Okay, of a regularly shaped solid and of a irregularly shaped solid which sinks in a liquid. Volume by displacement, including appropriate calculations. Okay, how do you measure the density of a liquid? So you just take a measuring cylinder, right? Measuring cylinder has been found, and you just pour the liquid inside here. You pour the liquid, then you count what is the volume of the liquid. Let's just say 50 cm cube, right, is your volume. Centimeter cube now, not meter, centimeter cube. And you know the volume, then take this take this liquid, transfer it to a bag or something, right? A bag with that has no weight and whatnot, or a beaker that has less weight, and then put it on the digital balance, right? Digital balance acquired, we put it on the digital balance, we measure it. Let's just say it is 2 grams. Then we find out the density. Density would be mass by volume. Mass is 2 grams and divided by 50, which would be our volume. So what do you get? 1 by 25 gram per centimeter cube, right? We use what? Gram, and we use centimeter cube would be my volume, gram per cm cube, sorry. So the units we use will be the units we get. So gram per centimeter cube. Normally the units will be kg per meter cube. Do remember in your exam you have to take this and convert it to kg per cm cube. I think yeah, that is about it. kg per meter cube, I mean, sorry. In your exam you always use kg per meter cube unless it is stated in the question that the answer should be given in, let's just say, kg per meter cube, right? Unless mentioned in the question. Describe how to determine the density of liquid. Achha, we got that. The liquid, how do you measure it? You first measure the volume of the liquid using a cylinder, measuring cylinder. Then you find out the weight, and you only need two things: weight. Let's just say you have volume and you have density. You can find out the mass. You have density and mass. You can find out the volume. So there are three unknowns, right? Call this x, call this y, call this z. You only need any two of this to solve this equation and get the third unknown. If you want to think about it in math terms, right? In math terms, this equation has three unknowns. So you need two of the information to find out the last one. Let's continue. Regularly shaped solid. If it is regularly shaped, that means that it is, let's just say, a cube. A cube like this, or a rectangle, anything, a sphere, anything that has a formula. Let's just say pi 4 by 3 pi r cube, right? This will be my sphere, 3D sphere, right? You can use this formula, find out the area, or sorry, volume, find out the volume, and then just take it on a digital balance and measure the weight. Then you can find out the density using this formula. So this is what they mean by a regular shape or regular solid. Regular meaning it's something you can use with a formula. It has a formula for volume, for surface area. What do they mean by irregular? So let's just say a piece of bending rock and whatnot. This is a three-dimensional rock, not 2D. And this rock has no formula. How do you measure the volume of this rock? You take a measuring cylinder with water inside of it. Yeah, there is a bit of water. You take the rock, throw it in, and then the measuring cylinder will look like this. The water is up here and the rock is up here, inside here. And as you can see, the level was, let's just say, at 1 centimeter. The level now is at 3 centimeter over here. So the water was displaced by this rock. And now you might see how we find out the volume. We take the volume before and subtract it from the volume after. So 3 minus 1. The volume after is 3. And we get 2 cm cube. 2 cm cube is our volume of this rock. And this is how you subtract. So volume by displacement, including appropriate calculations. Calculation meaning, that you have to subtract one volume from the other volume which you get after. And once you find out the volume, again take a digital balance. Measure the rock mass, let's just say 1 kg, and then plug it in the formula. Boom, done. And more or less, this is the amount of, this is the type of questions you will be getting. Not that much harder than this. Now let's see the notes. You can pause if you want. I'm just skimming through, not reading aloud. And this is how they, volume by displacement. It was 600 before. When you throw in the rock, it goes to 800 milliliters. So you know the volume of the rock. Okay, I think that is all. for chapter 1.3 and 1.4. Next will be actual chapter of forces, and we will cover this in a later video. So yeah, that is all for today, guys. Goodbye.